So let me have both ready for you. The GEMex, there we are. So please, everybody.
And the pointer?
And the pointer should be. Let me put on the pointer.
Okay.
How did you make this pointer, Volker?
The laser pointer.
My glasses, but
You want mine to go there? Yeah.
Oh yeah,
the top thing is pointer somewhere.
perfect.
Right there, right down
And then we take it over
there. Okay.
here. Yeah, okay. Okay, Walter.
Thank you.
Floor is yours.
Okay. Yeah. We're talking about geothermal and the presentation from Real Well and Geo360 and very interesting stuff. And Volker, I don't know, offshore, not so sure about earthquake being a big problem. Magnitudes 1, 2, 3 stuff, maybe. But to know more about where there are active tectonics, that's good. So John Zuta is the head of the Stavanger Labs for EOR SCOW, and I am up in Bergen in a group that is similar in terms of it combines a subsurface geoscience group with laboratory flow labs, actually. So okay, so we've been working on and off with the offshore, with the North Sea mainly, but the NCS, where it's hot, looking at the temperatures and saying, gee whiz, this would be great for geothermal. And maybe that's been going on since 2014, 2015, or something like that. So we've recently gotten serious, but some of this you've seen before in the 360 talk. You saw this mainland geology. Heat flow diagram, and from Christophe Pascal when he was at the Geological Survey. It's pretty cold on mainland Norway, although we've heard from Ever that they think it's quite good for the Everloop in places where you have a gradient which gets up to about 3 towards 25, and that's essentially where the red dots are there. Estimated temperatures at 5 kilometers depth, you see over here. So red is the estimated temperature at 5 kilometers being 150 or so. So once we can drill economically down there, closed loop would be really great. So the North Sea, many areas in the NCS are significantly better. And I'll come back to this. I guess I shouldn't use my hand here. I'll come back to the table in another slide. If we look over on the bottom right, you see where it's red, it's hot. The left-hand diagram on the bottom right these are from Yuri Maestrenko, also at the Norwegian Geological Survey. That's an estimate of temperature at 2 kilometers depth. And about heat flow, stratigraphy, different thermal conductivities, heat flow, it allows us to predict, which is a very important thing. But if you're talking about drilling down into a big Brent aquifer or sub-Brent, you've got all the water in the world and the temperature is what it is. So on the right, 7 kilometers depth. I'll come back to that. That hooks up well with this table, just a few fields, but it'll be bigger and so you can see it better. Okay, here's the table. The fields here are ranked in geothermal gradient. Highest geothermal gradient at the top. It does get higher than this in places, but 53 degrees per kilometer, starting at the seafloor. So all the depths you see here, water depth, of course, starts at the surface, but the other depths for reservoir here, reservoir, okay, reservoir depth meters relative to the seafloor, below the seafloor. So what we've done here using the NPD fact sheets is just to say, here are some example reservoirs which are quite positive for geothermal, for direct use of heat. And you see that as the reservoir temperature. It's approximate, it comes from the fact sheets. We have not gone into detail into the DSTs and data for particularly good temperatures. So that's the reservoir. All those temperatures, even with 10, 15 degrees of cooling as the water comes up to a platform, are good for most of what you need for the platform heat. There are some processes for separators which require maybe a bit more heat. But one of the points here is that if you electrify the platforms, get rid of the gas turbines, the process heat for the separators comes from the waste heat, most of it, on the gas turbines. So you're going to be using electricity to generate heat, as well as for the rotating mechanics. That's about 20%. So if you use direct heat, you can, in a typical platform, cut the electricity demand from land, from offshore wind, by 20%, plus or minus. Now, 200-degree isotherm. That's really nice for ORC electricity. If you take Tombar, the first red circle, below the reservoir, if you drill about 300 meters, if you take a well which is going to be taken out of service, plugged in or abandoned, and you deepen it by 300 meters, you're in 200 degrees. You're going to say, but it's not that simple. It's not that simple. Those wells in the HPT fields, the gas wells and the oil wells, they're 5 or 6 inches in the lower sections. You can't get enough fluid to generate 10 megawatts, 20 megawatts with that. You have to bore it out wider, 9 5/8 or 13 inches to completion, and in cases deepen it. The other thing is the wells, of course. Well, we'll come to that next. Let's see. So here we have Uri's two maps. 2 kilometers for the upper section, 7 kilometers for something deep. Very schematic, not correct diagram, just to talk about what will have to be done with wells, how you might reuse a well. Between the W2 and W5, so I've just sort of numbered the wells from left to right. So you have the platform, you have slots, you have wells, which are injectors. That blue one is an injector. The green one is producing. The idea with the one in red is that you've made a closed loop system by taking an out of service producer or injector, drilling deeper. The black line indicates roughly, where the conductor casing is, the production casing is. So it ends somewhere. You can expect that where the red line begins, you're going to have to turn it black. You're going to have to bore it out to a bigger diameter if you're going to generate electricity. If you're just generating using the reservoir water for direct use for heat, you can probably stay with 6 inches or something. But that's one of the things in this project. Okay, this is a proposal we're sending into NFR.
2 minutes.
Okay, I'm going to go a little bit longer with this and a little shorter on the second talk. So I show 3 levels of reservoir. I show the reservoir, which is the one with the green oil in it. And then there's, to the right, a higher aquifer. So if we use the reservoir for direct heat, we have to be very careful. We don't want to disturb reservoir pressures if there's still production from the reservoir. So it would have to be a balanced system or a closed loop. We might get sufficient heat from an aquifer above the reservoir and stay out of the reservoir, the aquifer lakes of the reservoir. So that's something else we're looking at in this project. It's an interesting thing about the table that was ranked in terms of geothermal gradient. The HT fields have the lowest geothermal gradients. So, but they do have overpressured water. So if you do go for a deep aquifer, or when Kristen's got no more oil, no more petroleum coming out, you use Kristen. You've got hundreds of bars of overpressure. So a possibility, you don't have pumping costs, and you can perhaps use the kinetic energy. So you can generate with the kinetic energy as well as the temperature. Okay. To move on, okay, this is a proposal. It's going to be sent into NFR as a KPN. We are, of course, more than happy to hear interested parties with cash. It's for energy transport and the low emissions. What I will say here is that in the blue in the middle, you have to hit the criteria in the call for proposals. And so we do that. Energy transitions, impacts on society, for example, renewable electricity, decarbonization. And that goes in a few weeks on the 15th of February. And if we are successful, we'll have a project start in mid-year July or a little bit later. So the scope, we're not focusing on just the Norwegian sector. We're also focusing on the UK sector and the Danish sector, because for companies, it's one big market. The real question is the cost. Is there a good business case for it? So I won't go into the details here. I'll skip through them, but the real point of the proposal we have, the project, is to see how it compares to electrification from offshore wind, from land power, and that there are direct costs, which are the costs of modifying wells or drilling new wells. There are societal costs. Many of us are geoscientists. What happens if there's no more, there are no more fluids to work with in the subsurface? Electrifying the shelf will take 9 terawatts. And we read that in 2027 or something like that, even without that, Norway is going to, and Sweden are not going to have any extra capacity. So, and then there are the synergies with the transition to hydrogen, to CCS, to energy hubs offshore. This is a bit obvious, I guess, so I won't spend time on this, just to point out that there's the technological part in 1, 2, 3, and then there's the business cases and the regulatory aspects and the social science aspects. And I think any project would have to have that. It's been very quiet about offshore geothermal until now. The September, the deep Ocean 21 deep dive study, all I will say here is that geothermal is on the left in the long list of energy sources that the committee looked at. It didn't make the short list, but here's geothermal. Red is a problem, yellow is, yeah, okay, but not highly prioritized. But geothermal is here. So it has a low TRL offshore. I mean, it's TRL 7 in many cases onshore, especially where you're drilling into a well-known Permian Basin type in the US, a sedimentary sequence, which is well understood. No oil there, it's an aquifer, but you know the permeability. That's what we have offshore. What we don't have is a demonstration of doing it. And then, of course, there are the space requirements. If you're generating electricity, is Turbuda Mitsubishi ORP going to fit in the same space as a Siemens gas turbine? I think it will. So, okay, I've used up my time here. And well, this is also in the media here. This was the Anarcho piece on the interview with Roger Except. He has many good points, I think. We look at it in a different way, I think, than he looked at Kristen, but it's nice to see it also in the news. So, any questions here before I just show a very little bit about some other projects we're involved in?
Any questions or comments? I have a
Or
comment.
discussion.
Yeah. Well, we are investing public money, 200 billion per year in the Norwegian continental shelf. We don't want stranded assets.
Mm-hmm.
We don't want these investments to end up in the net zero. We can't consume and produce the amount of fossil fuels as we do today. That's clear. But we have made this fantastic factory offshore that can be used. And an oil and gas company in reverse, like the same scale of CO2 deposition, CO2 like storage is kind of definitely a way forward. But of course,
How are you going to power that?
exactly,
Offshore wind.
exactly. How do you power it? Where do you get the energy from?
Should offshore.
And we are
wind be
running out of-
peaking power or
yeah.
the base load?
So I think, yes, all these questions, right? Yeah. So the point is basically, how do we move forward?
Mm.
So I think this project is really is perfect timing. Utvikle, ikke avvikle. What does that mean? Well, this is utvikling. Right? This is new ideas, new developments going forward.
The research council.
Yeah.
Yeah.
Yeah, exactly. But you any other comments, views? Yes.
Just a clarification that these indicators where you said that the geothermal was scoring medium to low on different criteria, are these criteria from the research council or where did they
No,
come from?
no, this was a committee. It was a project run for OG 21 by DNV.
Okay,
And so there's a report, and when we we'll put the web link up to it for that report. And so I have the slides. I'll show you them later if you want.
Yeah.
But there's a good discussion of what has to be done for geothermal and for other potential clean energy sources to move them forward.
I think we stop here unless there are some urgent questions burning.
I will say, we've had some great discussions with Odfjell.
Yeah.
About these possibilities.
Yeah, I'm really happy to have you here.
John and I have been, John's been the champion of reusing, John Zuta reusing wells scheduled for PNA. And
then they're lost,
well,
kind of.
yeah, but what I would say, John and I had this discussion with Frederick and several others at Odfjell, and we sort of went into the first meeting thinking, what are they going to say? They know about drilling wells and what it costs. And Odfjell was saying, yes, yes, yes. There are possibilities, but we have to look at all the costs. So that's where it is.
Run
A few short slides.
You have
or
30
what?
seconds.
No, less than that.
Okay.
So just one thing, I don't believe you've mentioned it, so Odfjell is becoming a member of CGER.
Yeah.
So
You should have been there from yesterday.
exactly.
From
So
yesterday.
you are very welcome. I
Yeah.
want to make that point. We're very glad to have you on board. And with respect to the newspaper article of NRK, so CGER was actually the CGER board was involved in discussions there. Our feedback was that we needed exactly such proposals of research that you are presenting here. We didn't send in any citation or reference to ourselves. That was the conclusion based on the article. But our feedback was that we recommended strongly to look into this more closely. So more research is needed before we can conclude anything. And yeah, so just wanted to make that point.
Yeah. And then short on this, we're gonna give room for Tor Erik. And then Eivind in the end before lunch. So take it away. Walker.
Okay.
Then
Oh,
your second.
Okay, thanks. Yeah, it's up there already. Okay, great.
yeah, this is going to be very short. I haven't, because I had a good idea that I'd run over time on the offshore geothermal baby. I just didn't put details into this, really. So we had Norse was part of an EU project cooperation with Mexico on geothermal energy. Apparently, Mexican delegations had been coming to the EU saying, we want help. You notice my American accent. They apparently said to the EU, it's just not working cooperation with the US. I don't know why. Embarrassing. But we had a 4-year project, 10 million for European partners and 10 million for the Mexican partners. So there were 5 universities and a couple of companies in Mexico, and there were companies and universities in Norway. In Europe, in Norway, it was IFA working with tracers mainly, and it was Norse working on both, you see on the bottom, EM inversion with constraints from Monset and Sventveit, and we had fractured reservoir characterization, me, Ivan, Anita. I don't think, no, we didn't get our mathematical geophysicists to come to Mexico, but this is this is where we were, volcanoes all around. But where these 2 geothermal fields were was, to skip ahead, in the near Veracruz, all the way over on the right side, the youngest volcanics in the yellow is what's called the Trans-Mexican Volcanic Belt. The volcanoes are older on the left, younger on the right. So these weren't volcanoes, these were volcanoes which had collapsed into themselves. So they're calderas. One, Los Humeros, has the installed capacity of 40 megawatts. About 50% of their wells are dry. And then they've determined that it was too expensive to log new wells. So they don't really know why some are dry and some aren't. And what we were looking at is the regional tectonics for locating or figuring out where active faults were, because an active fault is keeping itself open, keeping itself permeable. And the history of that also. And the photo on the bottom right, which is the only field bit I'm going to show in this, we're not only looking at small scale fractures, but this is in a very young half graben in one of the geothermal fields. And we're looking at you get the sedimentologist who say, wow, look at this. How did you get these, this clastic layer over this very fine mud layer? There must have been a very sudden drop in the basin with erosion from the side coming in. Active faults. So we dated them with carbon dating. 10,000 years, 9,000 years, 13,000 years. So this is a key on land to say, okay, this is a fault. If we can follow this in the subsurface, that's a drilling target. Yeah, okay, there's a list of the European partners over here on the right. Most of them essentially, we have the ERA joint program for geothermal. And this is essentially all the partners in it. The partners who wanted to, not everyone is there. This is another EU project. It's the opposite of GEMex. It's not 40 megawatts installed power. It's not drilling to 3 kilometers, 2 kilometers and 300 or 320 degrees Celsius, dry steam. The idea here is that there are, Kenya's generating a lot of electricity from geothermal. They're becoming one of the world's biggest producers. But right next to their geothermal fields, the wires go straight overhead, and there are villages who have no electricity. So this is you might say, a pre-project. There's no drilling here, but the idea here is that in these villages, these tufa mounds are hot springs, steam coming out of the top, hot water coming out of the bottom. The middle photograph, you see a little puff of steam in the shadows in the lower part. On the right, behind the camel, to the left of the camel, you see water jugs, and there is in the afar here, there is no water, there's saline water, nothing to drink and nothing for your livestock, and they heard. So what you see on the left here is a little pit dug out and lined with stone with branches in it. It's a steam vent. And the Afari people have learned themselves, their traditional method of living here to collect water is to put acacia branches in the steam vent, but lined with clay so steam condenses. But geothermal energy, there's steam. We can drill a few hundred meters down. There'll be the hot water, direct hot water, superheated, will condense. We can condense it for fresh water. A little deeper than that, we can put in a few kilowatts, a few hundred kilowatts of ORC to combine with the heat. So there is electricity, but there's also the cascade of the thermal cascade for various direct uses. Drying agricultural products, well, their products are livestock, so drying meat or refrigerating meat, getting cool from heat. There you see in a satellite image, those are the steam vents, but the reason we see them is because they built little structures to condense the water. This is the case in Kenya, it's the Homa Hills at the northeast side of Lake Victoria. They have plenty of agriculture and there's fishing. And the geothermometers say that at maybe 300 or 500 meters, somewhere between high 60s and 150 degrees Celsius will be available. And the water on land here is saline, brackish. So they actually pump water from Lake Victoria, but they don't have electricity to do that, so they carry it. The women carry it typically and collect the firewood. So if we can replace that labor with fresh water in the village and with electricity for cooking, or if methane is coming out, maybe capture the methane, use that for cooking. We can, that half of the economy can participate in education and development. So this is done. This is a few Kenyans and a few French who have. Jacques Barret did his PhD thesis here, got very involved with the BRGM in geothermal and wants to come back here. I mean, is coming back here, but this, you see the community meetings above, which is in Ethiopia, and the community meetings below, which is in the Homa Hills area in Kenya. So the other point is the tradition, find out what's wanted and what's needed. This isn't to generate electricity to send back to Nairobi. This is to follow traditional practices. Okay, I will stop there. Good, black screen. Okay.
Perfect. Thank you. Yeah. Working with energy systems has several applications. Shirley, are there some comments before we move on for Eric? Questions? We are 2 minutes behind schedule.
Yeah, what Norse is doing here is the geoscience and making the models, working on the models for and the risk for drilling here or there, and working on the energy system. So the energy systems cascade use. We have 2 energy networks. One is thermal water and the other one's electricity. We're not involved in the other parts of the project, which are social sciences and capacity building. Yeah,
Thank you, Walter.
sure. And as you can tell, I'm happy to talk for hours about this.
So yeah, I guess you will bring us back to ground, Norwegian ground, Erik?
I think so that I could speak English, but I prefer to do this speech in Norwegian. Vi har noe med at vi jobber i Norge, og vårt hovedmarked er Norge, Sverige og Finland. Mitt navn er også Tor Erik Museus, jeg har jobbet med geotermi siden 2006, og det som er interessant å observere i den perioden, det var også at jeg satt